Okay, now, real quick, what happens if r is greater than 1 or less than negative 1? Just think. What's going to happen here? I'm not even going to use this equation. Just think. If I take a and I add it to a number, which is a times r, but r is larger than 1, what's going to happen to this term? Remember, this guy right here is a1, this guy right here is a2, really, theoretically. It's just I know it's confusing and convoluted, but you'll get used to it. There's a simpler way to deal with it, particularly in calculus. All right? Well, I know that ar is going to be greater than a. I know that ar squared is going to be greater than ar. I know that ar cubed is going to be greater than ar squared, etc., etc. What's going to happen? This number is just going to get bigger and bigger and bigger. Even if r is, let's say, less than negative 1. Let's get over here again. So I got s of n equals, I'm just going to write a because I'm not because I'm being lazy, but just I'm simplifying the notation. 1 minus r to the n over 1 minus r, and I know that my sum is a, this is as k goes from 1 to infinity, and I'm going to go a r to the k minus 1. All right, so now we're talking, this right here is called an infinite series. An infinite series. I think I mentioned that before, but if I haven't, there it is. All right, now again, we know 1. If absolute r is less than 1, this implies that s equals a over 1 minus r. Guaranteed, free of charge. 2. If r is greater than 1 as opposed to 0. If r is greater than 1, then what's going to happen? Well, for every time that I multiply through, or multiply ar by a number that's greater than 1, right? I know this thing is going to diverge. Diverge. Oh, by the way, this converges. Throwing all sorts of new vocabulary at you. All right? It's going to diverge. How about 3? What if r is less than 1? Same thing. It's going to diverge. Because what's going to happen is it's going to be exactly the same thing as when r was greater than, less than 1. Sorry, guys, I'm not focused. It's Sunday night. I came in here to finish this up. If r is less than negative 1, what's going to happen is the same case. I mean, look at what happens. If I have a times r to the k minus 1, well, here's what we get. We get a plus ar plus ar squared plus ar cubed plus dot, dot, dot. Now, remember, to get from here to here, I multiply by r. Here to here, multiply by r. Here to here, multiply by r. If r is less than 1, the only thing that's going to happen is it's going to go plus, and then it's going to change the sign to a minus. The next one's going to be plus, then it's going to change the sign to a minus. But the numbers are still getting bigger and bigger and bigger and bigger. It never converges to an actual term. Now, think about this one. What happens if r equals 1? Well, doesn't that imply that my sum of a times r to the k minus 1 is just going to be, if r equals 1, I'm going to have a plus a plus a plus a plus dot, dot, dot. No matter how small, teeny tiny, infinitesimally tiny, teeny a is, if I add it to itself an infinite number of times, remember this is an infinite series, if I go 1 to infinity, I'm going to add it up an infinite number of times. Infinity is patient. It takes its time. Eventually it too will diverge. Now, here's kind of a fascinating case, and this is one I've argued with students ad nauseum about. What if r equals negative 1? Well, what's my infinite series going to look like? Okay, 1 infinity, a times r to the k minus 1. What happens? Well, my first term is going to be a. My second term is going to be negative a. My third term is going to be positive a. Minus a, plus a, minus a, plus a, dot, dot, dot. Well, what's going to happen? If I just take this first partial sum of a, I get a. The second partial, 0. Third partial, a. Where are we? Fourth partial, 0. So what's happening is I'm going from a to 0 back to a 0, a 0, a 0. Well, you may say, well, Ripley, why can't we just say that it converges to a? Well, because it goes to 0 on the next term. Well, then let's say it goes to 0. Nope, goes to a the next term. It never fully converges to a term. So this guy also diverges. That's kind of nice. That eliminates a ton of the real number line, right? Because we know it's only going to converge in this case right here. This is the only time it converges, is when absolute R is less than 1. Let's do one of these guys. All right, ready? So I'm going to do the sum as k goes from 1 to infinity of, let's go, I don't know, 4 times 3/4 to the k. Now, I'm doing this on purpose because you may be going, well, Ripley, wait a sec, this is crazy. It's supposed to have a k minus 1 here. I am so trained that I got a 1 here. Why isn't this a k minus 1? Don't freak out. That's your first rule. First thing you're going to do is you're going to factor out the 4. Let's get the 4 out of the sum. Get it out of our way. We'll play with it at the end, right? So really all I've got is 3/4 to the k, okay? So if I think about this, this can be written as 4 times. Now, what's my first term? What's 3/4? What's my next term? It's 9/16. What's my next term? It's 81/64, etc., etc. Now, we just used a funky notation to write this guy, but it's still geometric. This is just A1 or A, and then my ratio to get from one term to the next is just 3/4. Okay? So I know, look, first things first, what's A? A is 3/4. What is R? R is 3/4. Thank God, because if it weren't 3/4, it would diverge, right? Now this 4 is just along for the ride. So I know that this implies that my infinite series is going to converge to 4 times, and remember the 4 is just along for the ride, and it's A, which is the first term, 3/4, over 1 minus R, which is 3/4. So I end up with 4 times 3/4. Last I checked, 1 minus 3/4 excuse me, is 1/4. My 4's cancel. And who knew? Converges to 12. That's crazy. It's kind of fun. Now, we've all seen the proof. Well, maybe you haven't seen the proof. If I take a piece of paper and I fold it in half, and then I fold it in half again, and I fold it in half again, then that is exactly the same thing as saying the sum as k goes from 1 to infinity of 1/2 to the k. All right, now let's write out what this is. This is 1/2. Again, these are sort of arbitrarily chosen. The problem is there's an infinite number of ways to express this. I could start this thing at 15 and then have this thing start at 15 minus, I don't even want to think about how I'd have to set the thing up. It'd be a pain in the butt. It'd be what, 15 minus k? No, what, 14k? It would be awful. I can't even think about it right now. It's too late. But what we really got to look at is what's happening. I'm doing 1/2 plus 1/4 plus 1/8 plus 1/16 plus ... and that's it. Now, think about it. What is a 1/2 plus a 1/4 plus an 1/8 plus a 16th? Now, I remember when I first started doing this, I was like, well, it's got to go to infinity. I'm counting up an infinite number of terms. That's not necessarily true. And I'll show you here on a blank sheet of paper here in just a sec. Well, is it geometric? This is my first term. This is A, right? I'm going from one term to the next by multiplying by a common ratio, which is 1/2, which implies that my sum, my infinite sum, is equal to A, which is 1/2 over 1 minus 1/2, which is 1/2 divided by 1/2, which is 1. Now, let me show you. It's a real quick and easy graphical way of doing this. Oh, goodness. Oh, I'm going to have to show you on a different page. I'll show you on this page. I'm going to get rid of this since we've already played with this. Watch. I have one sheet of paper sitting right in front. I'm going to cut it in half, or more or less half, as a badly drawn half. Do you agree that that is 1/2 of the paper? More or less. Give me a break. Do you agree that this guy over here is 1/4? Do you agree that this guy over here is 1/8? This guy over here is a 16th. This guy over here is 1/32nd. Right? Half. See what's going on here? 1/2, 1/4, 1/8, 16th, 32nd. This guy over here is 1/64th. This guy over here is 1/128th, etc. Right? Etc. 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 1/2 plus a 1/4 plus an 1/8 plus a 16th, 32nd, 64th, 1/28th, 1 or 2, 1, 256. This is fighting with my, never mind, 1, 256, 1, 5, 12th, etc., forever is still going to be, it's still going to add up, all those fractions are going to add up to one piece of paper. That's always a fun sort of geometric way of displaying that series. All right, sorry about any confusion on that one. So what you need to take away from this lesson is you got to know the difference between a convergent and a divergent infinite series. And you got to be able to use, let's go back to our equation, if it's not infinite, remember, if it's a finite series, all finite series converge. This is for finite series. Notice n is fixed. I'm not going to infinity. I'm starting from k equals 1 and I'm finishing it in. But again, these guys don't necessarily have to look this way. They don't have to be in that relationship to one another for it to be a geometric series. And I know that's cause for confusion, but trust me, once you've played with a couple of these, you're like, yeah, I get it. I know what he's talking about. All right. Thanks for your time and attention. Have a fantastic day, and I will talk to you soon.